Okay, so this is a continuation of sequences and series, and we're moving on to infinite sums, okay? Or sums to infinity. I might cut this video short, I'm not sure. The markers have quite a strong smell, and after about an hour of doing this, I start feeling a bit spinny. But I'll try. I'll try to do as much as I can. So let's keep going here. So we saw the geometric. We saw the geometric series, and we saw that it had the form, okay, and the form was a plus a times or plus a or squared, all the way on forever. That's the geometric series, and this can be written in a kind of a compactified notation, where we use this symbol here. It's called sigma. And I can start this with an index. I'm not going to use that index, actually. I'm going to say that this is the sum. I'm going to let the index be I. Okay, and I'm going to go I from 0 to infinity. Okay, and then I have a or to the I. Okay, so this means sum of. Okay, this means I is an index which runs from 0 to infinity, and this says take a, multiply it by or, where or is raised to the power of the index. Okay, so it's the same thing here. Okay, and now that's the sum to infinity. Now that's another way that I can write this series. Now the question is, can I actually evaluate this? Can I actually come up with a number which is equal to an infinite sum? And the answer is obviously not always, but sometimes. Okay, not always. Okay, so sometimes okay, we can sensibly define a value of an infinite sum. Okay. Not always, but sometimes. And we'll talk about how that's defined. Okay? And we use the value as follows. Okay? We say that the sum, okay, to infinity, where I goes from, let's say, we can start at 0, we can start at 1, doesn't really matter. Okay, and I have a to the I, the ith term. Okay, I'm starting at 0 here in this case, but that's totally okay. This is equal to the limit as n goes to infinity of the sum to n. And what was the sum to n? The sum to n okay, we can write in this fashion: I goes from 0 to n of ai. It's a bit technical looking, but don't worry about it too much just yet, okay? And what this basically says is, I can take the limit of the partial sum Sn, and if I can come up with a sensible number in that case, then I can define an infinite sum as having a value. If not, then I can't. Okay? So let's look at the arithmetic series. The arithmetic series had the form that ai The ith term was equal to what? It was equal to it was equal to a, which is some starting value, plus, and then I have I minus 1 times a common difference. Okay? And we saw that the sum to the nth term was what? That was n over 2. Okay? And then I had 2a, and then I had plus n minus 1 times d. Okay? I'll just bring up some notes here to remind you of it. That was in the first video. Okay? And this was the formula that I ended up with here. Okay? So that was my formula. And now the question is, well, what happens as n goes to infinity? Okay? Okay, well, let's look at this. Okay? N is a multiplication term here. Okay? And even just looking at an example of an arithmetic series like I had here, we can see that the sums get bigger every single time because I'm adding on that constant difference to every term. The terms are always getting bigger. Okay? So as the result of this, we can see that this n here, okay, is actually going to go to infinity as n gets large. Okay? So as n goes to infinity, okay, Sn goes to infinity also. Okay, so for an arithmetic series, it doesn't make sense to talk about the value of an infinite sum. Okay, that's okay. This is fine. Okay, an arithmetic series is just something we deal with differently. We don't deal with the infinite sums. Okay. What about the geometric series? Okay. Well, the geometric series is a little bit different. Okay. So as a reminder, geometric series looks like this. Okay. We're going to let the ith term be, and what is it? It's some initial value. And then we have or I minus 1. Okay. And here, the sum to the nth value is a times 1 minus or to the n over 1 minus or. Okay, and that's always true. Okay, that's always true. This formula is always true. But what about the limit as n goes to infinity of Sn? Okay, well, that depends on one thing. Okay, and it depends on how big or is. Okay, if we look here, we can see that the bottom never really changes. Okay, the bottom is constant. Okay, so everything that's interesting is actually happening on top. Okay, so look there, I see I have the a, 1 minus or to the n. Okay, now a is a constant value, 1 is a constant value, but or to the n is changing. Okay, it's changing with the size of n. Okay, and there are two kinds of behaviors when I take powers. Okay, if or is less than 1, and here I mean the absolute value of or is less than 1, so it's allowed to be negative. It's just it has to have a magnitude smaller than 1, which means that minus 1 is less than or is less than 1, then or to the n goes to 0 as n goes to infinity. Okay? And what happens then, okay, is that Sn is going to go to, well, I'm going to have a 1 minus, this or to the n is going to go to 0, and I still have 1 minus or on the bottom, okay? And that would give me a over 1 minus or, like that, okay? So as n goes to infinity, I approach a particular value, and the particular value I approach is this value here, okay? So for a geometric series, with the following: minus 1 less than or less than 1, we have that the sum to infinity from I equals, we have to go from 1 in this case, because otherwise it would be starting off at minus 1. Okay, but I want to start off with a power of 0. So this is, okay, which is equal to the a plus the aor plus the aor squared, and on forever. That actually has a definite value, and the definite value is a over 1 minus or. Okay, but, okay, if or has a magnitude which is greater than or equal to 1, then we have a problem. Okay, then we have a problem. What's the problem? Well, first of all, if or equals 1, okay, this division here would be 0, and that doesn't work, okay, which would be a problem. But even if or is not equal to 1, and I'm not allowed to divide by 0, well, then the or to the n gets big. Anytime you have a number bigger than 1 and you take powers of it, it gets bigger and bigger and bigger. So then the sum goes to plus or minus infinity. I should say the sum doesn't approach any value. Okay. It could go to infinity, it could go alternating, switching between two values, that's entirely possible. That can happen. Or it could simply go off to infinity. We've no way of knowing, but it certainly doesn't approach a numerical value. Okay, so if we have this type of arrangement where we have or greater than 1, then we cannot approach a meaningful value. Okay, so let's try something here. Let's try an example. Let's evaluate and we'll have the sum of I goes from, we'll say 1 to infinity, and we'll take 4 times 1/3, okay, raised to the power I minus 1. Okay, so that's my situation there. So what does this look like? This looks like 4 by 1/3 to the 0 plus 4 by 1/3 plus 4 by 1/3 squared plus etc. on forever. It goes on and on and on. Okay, well, what I need to do is I need to identify my A and my OR. Okay, so it's pretty simple. Okay, in this case, A is equal to 4. Okay, and OR is 1/3. Okay, and of course 1/3 is between plus and minus 1. It's in that range. Okay, so this formula applies. So the sum to infinity, I runs from 1 to infinity of this expression here, 4 1/3 I minus 1 is what? Well, the A is going to go on top, that's a 4. And then I have 1 minus 1/3. Okay? And I'll get a value here. This is 4 divided by 2/3, which is 4 multiplied by 3 over 2. 4 multiplied by 3 over 2 gives me a total of 6. So I'm actually going to get the value of 6 by adding up these terms forever. Okay. Let me do another example, which is a little bit easier to visualize. Real simple this time. Let's say we want the sum where I goes from 1 to infinity, and all we have is 1/2 to the I. What does that look like? That's 1 plus 1/2 plus 1/4, all the way up, going on forever. So 1, 1/2, 1/4, next one would be 1/8, and so on. Well, here the A is just 1, okay, and the OR is equal to 1/2. Okay, and then I would get the sum where I goes from 1 to infinity of 1/2 to the I is what? Well, then I have 1 over 1 minus 1/2, which is equal to 1 over 1/2, which is 2. Okay? And this is pretty easy to visualize, actually, surprisingly. Okay? So say I have a number line here. I'll make it reasonably big. This is the number 1. Okay? And I want you to imagine what I'm doing here. The first step, I'm going to add on 1. Okay? The next step, I'm going to add on 1/2. So this is 0, and this is 2. Okay? The next step, I'm going to add on 1/2, so I get halfway between. Then I'm going to add on 1/4, which means I get halfway between my answer and 2. Next time I'm going to add on 1/8, which means I get halfway between my answer and 2, and so on. So as I keep doing this process of going halfway each time, halfway towards 2 each time, that distance gets smaller and smaller and smaller, and in the limit I'm actually going to hit the 2. Okay, and in the limit means when I go to infinity. Okay, which, so in the limit it converges to a value of 2. Okay. And of course, it's not always the case that series are going to converge. Okay, so we're going to want to talk about some tests for convergence, which we'll talk about in a little while. But I'm just going to stop the video here, and we'll talk about that in the next video. Okay, take care, everyone.